Today, we're diving into a hidden world. We're talking about the science of finding tiny, invisible flaws in the most critical parts of our world. Things like power plants, airplanes, long before they can turn into massive failures.
I mean, really think about that for a second. We built these huge structures. We fly at 30,000 feet. We depend on this stuff every single day. So how can you be sure it's safe? How do you actually check for weakness deep inside a solid piece of steel without, cutting it open and wrecking it?
Well, the answer lies in some seriously cool technology. We've figured out ways to literally peer inside materials, to scan their surfaces, and to find the tiniest imperfections that could cause some really big problems. Okay, let's get into it.
So what do we actually call this field of science? Well, it all falls under this one umbrella, NDE, or non-destructive examination. Yeah, sounds super official, right? And it has a definition to match.
Okay, that's a bit of a mouthful, I know, but every single word in there is crucial. See, it's not just about finding a flaw. It's about locating it, measuring it, and then figuring out what it actually means for the safety of that part.
But let's just boil it all down. At its heart, NDE is exactly this. It's a whole bunch of clever ways to inspect something for problems without damaging it at all. It's kind of like the ultimate form of quality control.
You can think of an NDE professional as a kind of detective. And just like any good detective, they've got a toolbox filled with specialized gear. You wouldn't use a magnifying glass to dust for fingerprints, right? Same idea here. You have to pick the right tool for the job.
And this is where it gets really interesting. Are you looking for a crack that actually breaks the surface? Well, an inspector might grab a method called liquid penetrant. Are you more worried about tiny little bubbles, what's called porosity, trapped deep inside a weld? That is a job for radiography. See, different kinds of flaws need completely different techniques to find them.
So let's pop open that toolbox and take a look at the first set of tools, volumetric examination. These are the heavy hitters, the techniques that let us actually see inside a solid object.
Now, the first one is probably a concept you're already familiar with, radiographic testing, or RT. Just think of it like a medical X-ray, but for things like pipes and airplane parts. You pass high-energy radiation through the component, and it creates a picture on the other side.
Now, to get a really good picture, these inspectors have their own special gear. The image itself, that's called a radiograph. And to make sure that image is sharp enough, they use this little device called an IQI. It's kind of like a built-in eye test for the X-ray itself. Then they use something called a densitometer to measure how dark or light the film is, which is how they spot a hidden flaw.
Okay, so the other major way to look inside something is ultrasonic testing, or UT. This time, instead of radiation, UT uses high-frequency sound waves. We're talking way beyond what a human can hear. It's pretty much the same idea as sonar on a submarine or a medical ultrasound.
So how does this actually work?
Well, an inspector uses this device called a transducer, which sends a little pulse of sound into the part. They use a gel called a couplant to make sure the sound gets in there nice and clear. That sound wave then bounces off any flaws, and those little echoes pop up on a screen as a series of peaks. That screen is the A scan, and an expert can read it like a map of what's going on inside.
So here's the bottom line. These two methods are great at finding different things. Radiography is amazing for finding stuff like porosity, those little bubbles, or changes in thickness. Ultrasonics, on the other hand, is super sensitive to cracks. One gives you a permanent picture, the other gives you live data on a screen.
Okay, so we've looked inside the material, but not all flaws are buried deep down. Some of the most dangerous cracks actually start right on the surface, where they can be practically impossible to see with your own eyes. So let's move on to our next set of tools in the toolbox.
One of the most common ways to check the surface is with liquid penetrant testing, or PT. It is such a simple but brilliant way to make microscopic cracks, ones that are open to the surface, just pop right out so you can't miss them.
The way it works is just beautiful in its simplicity. First, you cover the surface with this brightly colored liquid dye, and it seeps into any tiny cracks. Then, you clean all the extra dye off the surface. Finally, you spray on a developer, which is basically like a blotting paper. It pulls the trapped dye back out of the crack, and boom, the flaw becomes easy to see.
Another really powerful tool for surface inspection is magnetic particle testing, or MT. And as you can probably guess from the name, this one is all about magnetism.
Now, the catch here is that this only works on materials that can be magnetized, what we call ferromagnetic materials. Think of most steels, things a magnet will stick to. An inspector creates a magnetic field in the part. If there's a crack, it messes with the flow of that magnetism. Then, when they dust the surface with fine iron particles, those particles get drawn to the disruption, and they pile up right over the flaw, making it totally obvious.
Okay, we've talked a lot about all this cool technology, but honestly, these tools are totally useless without a skilled expert running them. The single most important part of any of these inspections is the qualified, certified professional who's making sense of all the data.
Take a look at this number, 400. What do you think that represents? It's not a price, it's not a measurement, it's time.
This number just perfectly captures the dedication involved here. 400 is the minimum number of hands-on experience hours you need just for one certification, a level 2 radiographer. And that's on top of all the classroom training. The standards are incredibly high for a reason.
So the whole industry is structured around 3 main levels of certification. A level 1 can perform tests, but they're following very specific instructions. A level 2, that's your experienced pro. They can set up the gear and, most importantly, interpret the results. And then you have a level 3. That's the expert, the person who can actually write the procedures, train everybody else, and has the final say.
And really, this is what it all comes down to. You see, the blips on an ultrasonic screen, the shadows on an X-ray, they're all just data. It takes a highly skilled human being to look at that data and find the truth that's hidden inside, the truth that keeps us all safe.
And all this leaves us with a really fascinating question for the future. You know, as we invent stronger, lighter, more complex materials, think 3D printed jet engine parts, advanced composites, the flaws are going to change too. The real challenge for the next generation of these inspectors will be to invent brand new ways to see a whole new kind of invisible.